Bloom filters and simple payment verification schemes. So what is a Bloom filter? A Bloom filter is a probabilistic data structure where you can add elements and then test whether an element has been added to the filter. So here, for instance, let's add address 1 into the filter. We do so by taking the hash of address 1 and then flipping the bits in the filter where appropriate. Then we do the same for address 2, we hash it and we set the bits for address 3, etc. Now, in order to perform a membership test, we do the same. We hash address 1 and we see whether this is actually, these bits are matching. For address 1, that's true, it's a true positive. Now, if we hash address 4, it happens to be that the bits of the hash that we get are those here. And that's a false positive, right? The membership test tells us address 4 is in the filter while it actually isn't. So a Bloom filter can specify a false positive target rate. And this is like a rate that the filter should adhere to. And address 5 here we can see if we hash address 5, then we flip this bit and this bit remains 0. Which means this element is actually not in the filter, and this is good because we actually have a true negative. Now, how can we use Bloom filters to filter transactions that are relevant for a particular user? Well, so let's say we have an SPV client here, we have a full Bitcoin node here. So what we can do is we can extract these particular addresses of the wallet and we can insert it into a Bloom filter. Now, once we perform a connection with a full Bitcoin node, we can also transmit the Bloom filter that we just created, right? And this Bloom filter kind of encodes what we're interested in. So the full node, upon reception of a particular transaction, it will say, so is this particular transaction relevant for the Bloom filter? And if it is, it will send the relevant transactions towards the SPV clients. Now, there will be some false positives, right? Because Bloom filters yield false positives, but that's fine. And it's also, the false positive rate is something that we can specify and parameterize. Now, what about if this full node is an adversary, if it's a malicious node? Well, the Bitcoin developer said we approximate to around 33 million addresses in the blockchain. This is actually quite a while ago. The target false positive rate is 0.1%. So in that case, the user addresses should be hidden among 33,000 false positives, which should be a high enough anonymity set. Well, that's the promise. Now, in order to verify this promise, we have this following model and privacy measure. So we have an SPV client here, and we have a blockchain. We have an adversary that runs a full Bitcoin node, and the SPV client connects to this particular adversary. The Bloom filter is parameterized with a set of parameters such as the seed and the target false positive rate. We take all the addresses of the blockchain, we perform a brute force search and get a total number of positives. Right? These are yielded from the Bloom filter. And then we know, because we have set up the SPV client, we know the number of addresses that the addresses actually that the SPV client owns. And this is the set of true positives. Now, we can quantify privacy by comparing objectively these two sets of addresses. And then we can increase the number of addresses and do the same thing again, right? We can add here more addresses and repeat the whole cycle. And then we can even do this with a second Bloom filter in order to try to see whether we can do any intersection attack among different filters. So what we've seen is the SPV client implementation for the Bitcoin clients currently do a so-called stair stepping. So the Bloom filter is designed for a maximum number of addresses. So for a bunch of addresses, like I think it's 50 addresses, and for a target false positive rate. And this target FPR is only achieved once the maximum number of addresses are inserted in the filter. So that's a problem, because if you insert less addresses into the filter, you will not achieve this target false positive rate. But okay, So we have here one Bloom filter because we added some addresses, right? And then we add another address, we get another Bloom filter, etc. So once we exceed the maximum number of addresses, we resize the Bloom filter. So then we get, for example, a bigger Bloom filter. So you can see here, once we have 50 addresses in a filter, we go up to 100, we go up to 150. And there will be like different Bloom filters that are proposed. And what we can recommend from a privacy perspective, you should always avoid filters with different sizes, because these filters, these three different filters, they will yield different false positives. If you have two filters that yield different false positives, you can basically do an intersection between them and outrule any false positive, likely any false positive. So unfortunately, so you create a filter for max addresses, but you insert less. So the actual false positive rate is quite inferior to the target false positive rate, as we will see in the analytical results. So here we can see how the actual false positive rate and target false positive rate don't match, right? So up to 50 addresses here, you can actually see, right, like around 25 addresses, the false positive rate is really low. It's like almost 0%. And only at the very end here, it reaches this target false positive rate of 0.05%. What's interesting is the more number of addresses we have in the wallet, the closer it kind of gets here. But do you know anyone who has really 500 addresses in their Bitcoin Android app? I don't. Okay, so yeah, we can see here that over time this evens out, but at the beginning, I think the most critical part is here, where most users are situated. Probably most users have less than 20 addresses, so the effective false positive rate is almost 0. Now, regarding this resizing, right? Once you achieve a maximum number of addresses, you want to get a bigger filter, and the hash functions they are adapted to fill space of a new filter. So, which means that these filters, they yield different false positive. And as I mentioned, this allows you to do intersection attacks. One thing is that these filters, they also use a seed value for the Bloom filter. So, and if the seed value changes, then again, you have a filter yields new or different false positives. So this is something to be avoided. So the summary of the current SPV design choices is there's some stair stepping. So the actual false positive rate is really inferior to the target false positive rate. We experience resizing, so there are different false positives. And there's a restarting, and the client doesn't save the seed values, and therefore the filters produce different false positives. So given one Bloom filter, we find, given these findings, we can actually, the likelihood of identify an address of the client is quite high, right? So the probability of correctly guessing an address is quite high. So the likelihood of guessing all addresses is not that high if the user here has more than 25 addresses. So this is the probability of correctly guessing one address, and this is the probability of correctly guessing all the addresses in a wallet. So it's true that this part is probably the most interesting because many people don't have that many addresses. So what about multiple Bloom filters now? So if you have one filter that yields these positives, another filter that yields these positives, and another that yields these positives, we can do an intersection and discard any false positives that don't occur in multiple filters. So in order to perform proper experiments here, we have done the following without a resize. So the experiment is we have no resize, the same seed and the same size. Okay, so in that case, we have here a Bloom filter. We get these addresses. We add an address, but we don't add enough addresses to trigger resize. So we get here some additional positives, kind of. And then we do an intersection between them. So our results are that basically here P of 1 with one Bloom filter is 0.29, right? And if the target false positive rate is bigger, if it's, for example, 0.5%, then this is relatively low. So if we use 2 bloom filters, we can see that it's slightly higher, right? Here. So there's, but no real change of privacy, right? They yield almost the same positives because there was no resize of the filter itself. So the adversary does not really learn very much. Now, if we do perform a resize, this means there will be a different set of false positives, right? You can see this here. Then the probability with one bloom filter to guess one address with one bloom filter is 0.03, and the probability of guessing one address with 2 bloom filters is almost 98%. Right? So there's a significant change, and this means different bloom filter sizes improve the intersection attack quite a bit. So what about a restart now? So if we can take a bloom filter, we restart, so we generate a new seed, well, again, we will have different false positives. So we see the same result, right? The probability of guessing one address with one bloom filter is relatively low at this target false positive rate. The probability of guessing one address with 2 bloom filters is almost 99%. Okay, now one more experiment. We take a bloom filter, we add 50 addresses, which changes its size, right? There's an increase, there's a resize, and we do this several times, and so we do an intersection among all of these. And given this data set, we can basically guarantee that with 3 or more bloom filters, we almost identify always the addresses of a particular lightweight client. So we can guess all addresses of the client, right? So if we have 3 bloom filters, all addresses yielded by B1 addresses of this particular filter are leaked. So what we need a constant false positive rate. Well, there should not be like any ambiguity between a target false positive rate or an actual false positive rate. So we should certainly avoid multiple bloom filters with different parameters, and SPV clients should keep state, so we should save the state. So one proposed solution is that you pre-generate filters. For example, if you want to use 100 addresses, well, why don't you generate 100 addresses, insert them in the filter, and this is what you outsource. If you need more than 100 addresses, you do the same again. You have then multiple bloom filters, all with the same false positive rate, which is not changing over time. So these are pre-generated Bitcoin addresses. Obviously, you want to keep the state for the outsourced bloom filters, and the overhead is relatively small because these filters are not that huge. So given our measurement, the probability of guessing all addresses is nearly 0. There's no count, there's no stair stepping and nothing, and we're good even here in this critical phase where you only have a few addresses. We're safe. So as a conclusion, the information leakage through bloom filters in SPV client is a critical issue. So if you have only one bloom filter and less than 20 Bitcoin addresses, you can basically link all the addresses. If you get access to more than 3 bloom filters with different seeds or different sizes, then you can guess all addresses of the user with nearly 100% accuracy. So we proposed a lightweight countermeasure, which shouldn't be too complicated to implement, just a few changes. And using bloom filters for privacy is delicate, but I think it can be used if applied carefully. Thank you very much for your attention.